My name is Elizabeth Ramirez, and I am a part of Heatwave Team 15. My team and I will be presenting our project Thermal Heating Sleeve Unit, also known as THSU. Next, I will show you what the sponsor is like. Our sponsor is QO Plus. Our mentors, Patrick Benavides and Dr. Donald Peterson, helped us with the idea of this project, and through QO Plus, we were able to meet with veteran Sarah Fraser Kim. Sarah is now a para bobsled athlete. Sarah's main concern is her residual limb experiencing freezing conditions and poor circulation when she is competing in extreme temperatures. As a result, we were motivated to innovate this product for her. On the next slide, we talk about what is THSU. THSU is a compact prosthetic accessory. It will allow for a full range of motion for the user and delivers heat to the user's socket that helps blood circulation. It also has an adjustable heat output that is determined by the carbon fiber layer of the socket. Lastly, the temperature sensor reads the surface temperature of the sleeve so that it may adjust the heating output. Next, we talk about how does THSU work. The major functions of THSU includes the internal temperature sensor that sends data to the microcontroller. The MCU system regulates the power output by toggling the switch when the sensors read below temperature threshold. We also have rechargeable power supplies for both the MCU and heating elements. Now, my colleague Tharangini will talk more about the sleeve.
Thank you, Annie. Once we were given the project by QO Plus, we discussed with Sarah on the initial guidelines of the sleeve, leaving us with our original design. In the design, we initially wanted the heating elements in direct contact with the user's skin and wanted to embed the heating elements into the liner beneath the socket. For our final design, after having discussions with Dr. Ferguson and the mentorship of Dr. Benavides and Dr. Peterson, we changed the design to have a neoprene sleeve that is similar to an adjustable knee brace. Instead of having the 4 heating elements in direct contact with the user's skin, it will be embedded into the neoprene sleeve, which will be shown in our demo. The neoprene sleeve is in between the silicone layer and the carbon fiber layer, which is the outermost layer of the socket. By doing this, the heating elements will be distributing the heat in the prosthetic socket and not on the user's skin. On the next slide, we have our challenges and solutions. One of the challenges that we faced was a limited space between the silicone and carbon fiber layers of the socket to house the 4 heating elements and the temperature sensor. To resolve this, we used a 1 millimeter thick neoprene sleeve, which is made of a thin, water-resistant, and fire-retardant material to have our embedded heating components and the temperature sensor. Another problem was the PC board, batteries of the microcontroller, and the heating elements are too big to house within the neoprene sleeve. Due to facing this problem, we had a meeting with Dr. Ferguson, who gave us a solution of him creating a custom socket which can house the power supplies and provide space for the required wiring, which will be shown in the following slide. Here in our next slide, we have our demo.
This is our thermal heating sleeve unit, also called THSU, presented as a carbon fiber socket of an Autobot X3 with the microcontroller and rechargeable batteries embedded on the outside. The socket has an inner layer of silicone with a mid layer we created that is made of an adjustable neoprene sleeve. The sleeve consists of 4 heating elements across the leg and a temperature sensor that gives feedback to the controller to ensure the heating elements are given off the right temperature.
Here we are going to measure the voltage and the temperature as a function of time. While we are going to do this, I am going to test out the voltage indication system. As you can see, the temperature is rising as time is going. And as we are going to zoom out, I am going to turn off the battery for the heating element as the microcontroller is reading the voltage every 5 seconds. Look here. It is reading 0, and then the LED turns on to indicate that the battery is done.
This is our
This is a brief overview of our design process timeline. As you can see, most of our planning phase took place through the fall semester, while our design adjustment, validation, and testing took up most of our spring semester. In the next slide, we'll talk about costs. As you can see, the most expensive thing was the labor costs for commissioning a seamstress. However, if this was manufactured on a larger commercial scale, we would be able to bring these production costs down dramatically. Next, we'll discuss our team members and our contributions. First, we have Elizabeth Ramirez, who served as our team leader and project manager. Then we have myself. I served as our technical writer and our documentation lead. Christopher Reyes was our lead hardware engineer and our main programmer. and Therangini Balasekar, who was our lead researcher and our secondary documentation. Here's a bit about our sponsor. They're a nonprofit organization called Quality of Life Plus. They work along with university students in order to develop assistive technology to help the country's wounded heroes and improve their daily lives and aid them in getting back into the workforce. Now I'll hand it off to my colleague, Chris, to discuss future developments for our project.
Thank you, Rosemary. Our future improvements are as follows. As far as the aesthetic, we want to develop a smaller battery pack. We also want to compress the design by using neoprene material. Conceal wiring on the sleeve surface while keeping the removable aspect of the components for wash and care. On the technical side, develop a mobile application which allows the user to fine-tune the heating temperature. And as far as documentation, of course, we need to go for that patent. Final thoughts on this. In short, this project has taught us a great deal about working together under various constraints, including a global pandemic. Our hopes are that the product will make its mark on the daily lives of amputees and usher a new era of excessive innovation to help close the gap of limitation for amputees. Acknowledgements. We'd like to thank our professor, Dr. Patrick Benavides, Dr. Donald Peterson, Sarah Fraser Kim, and Dr. John Ferguson of Brooke Army Medical Center. Thank you, and this will be the time if we have any questions. As I go to our next thermal heating sleeve unit poster board. Thank you.